Hey, Kinsley. So I have some notes here. I'm going to talk through a couple things. Hopefully, this little bit of explanation and examples will make sense. And then I'll share this document with you, not necessarily the one I'm writing on, but the Google document. You can look through that and have that. But then, if you want me to, I can reset the quiz. You can ask some questions, and then I can reset the quiz. You can work through that. So if we look at this, I'm going to scroll just for a moment here, but if we look at this, all I've really done is taken notes that I've given in the past from arithmetic sequences, and I added the geometric sequence stuff to it. So um, I will walk through these pieces and try to explain some things, and hopefully this will be helpful. So I'm going to highlight first here that when we're looking at a geometric sequence, then we want to know that we are generating each term by multiplying a non-zero constant. We're multiplying some number that can be, you know, 10, 22, 5, whatever it is, or it can be fractions, one half, one third, two thirds, whatever. And so this is going to cause us to have some exponential growth. So if the number we're multiplying is greater than one, then the terms are growing, they're getting bigger. If we're multiplying by numbers between 0 and 1, then we are generating exponential decay. The values are getting smaller, they're approaching 0 usually. So we call that number that we're multiplying by the common ratio. That's here as well. So there's the common ratio. Some examples here. I'm going to switch to green. If you want to test, is a sequence geometric, then you just take one of the terms and you divide it by the term before it. So 15.5 divided by 31, that's one half. We would continue to test. You want to show that the number, the common ratio, that there is a common, meaning it's the same for all of them, a common ratio, that if we look at each term and divide it by the term before it, we will always get that same number. So 31 divided by 62, that's also one half. It supports our theory that the common ratio is one half. 62 divided by 124 is one half. 124 divided by 248 is one half. So because we have divided each of these terms and we ended up with one half, we say that this is a geometric sequence. It really only takes one value to be off for something to not be a geometric sequence. So let's say a common ratio was 2 and we started at -5. So if I multiply by 2, I would get -10. Multiply by 2, I get -20. But then let's say I end up with -30 for this term. And then I multiply by 2 and get -60. This is not a geometric sequence because that one term, -30 divided by -20, is not going to give us 2. All of the others that we divide would. And we could show that. We could say, look, we're multiplying by -2. We're multiplying by -2. This one only multiplies by 1.5. As soon as you see that you're multiplying by a different number, then we know it's not geometric. The other trick that math teachers or Apex, assessments will play on you or try to trick you with is that they'll give you an arithmetic sequence. They'll give you a sequence like this, and you'll recognize right away, oh, look, I see a mathematical pattern. I'm subtracting 3 each time in your brain, because you're looking for patterns, right? But you want to make sure you're looking for, are the numbers multiplying? So that's one of the common distractors that math teachers and textbooks will put into a problem that we're asking you, to select all of the geometric, and then we put an arithmetic in there to trick you. So that's one of the things to watch out for. I'm not sure if that happened in Apex or not. So the nth term, so just the formula for a sequence follows this pattern that if you wanted to generate a term of the sequence, that a sub n means any term. The 10th term, that would be a sub 10. The 100th term would be a sub 100. But so in order to write the formula, we have to know the first term, that's a sub 1. We have to know the common ratio. And so everything else in the formula just stays what it is. So we're going to replace a sub 1 with a number, and we're going to replace r with a number. So back to that example we had above, the 248, the 124, we determined that the common ratio r equaled 1/2. We look at the first number in the list, that is a sub 1. So that's a terrible 8. So that is a sub 1. So that means then that when we write our formula, so if I come over here and I write a sub n, so in order to generate any term that you want from the list, we would need to have the first term multiplying by the common ratio raised to n minus 1. So if you wanted the 20th term, then you're saying that n is equal to 20, and you would have a sub 20 equals the first term, 248, times your r value, 1/2, raised to the 20 minus 1. All right, so here's why that's important. You're moving from the first term to the 20th. The first term to the 20th, that's 19 terms apart. So that's why we're multiplying the 1/2 19 times, right? 1/2 to the 19th is 1/2 times 1/2 times 1/2, 19 of those. So that's the other, like the other trick that they can play on you here. Instead of giving you all of the terms of a sequence, so a question might say, what is the formula from the sequence given all of these terms? So if they give you the terms, then you go through the work of testing what is the common ratio, and you would say, okay, I know that r is equal to 5, and you could prove that, right? You would say, well, the 250 divided by the 50 is 5, and the 50 divided by 10 is 5. 10 divided by 2 is 5, right? So if you're testing or if you're just checking, what is the common ratio, you divide every term, and if you get the same number every time, then that is your common ratio, r equals 5. And we would have to know the first term, a sub 1 equals 0.4. So if you wanted the nth term, that's what that's called, the nth term. Remember that that's just the first term multiplied by r raised to n minus 1. So we would say a sub n is equal to 0.4 times 5 raised to the n minus 1. So that is then the nth term. This is the formula that you can use, and some people put parentheses around the r value just to make it clear that this is multiplication between the 0.4 and the exponent only applies to the ratio 5. But this is your formula. The way that we can get around that, or maybe you could look at it this way, the way I could make this problem a little tougher is to tell you the second term and the fifth term. So I might say, look, the second term of this sequence is 2. The fifth term of this sequence is 250. So here's what we would know, and sometimes a visual model makes this a little more clear. A sub 1, and then we have 2, and we've got a sub 3, then we've got a sub 4, and then we have 250. And so what we can see from writing it out this way is if I multiply the second term by r, I get a sub 3. Multiply the third term by r, I get a sub 4. Multiply the fourth term, and I will get a sub 5. So what we see then is that the second term, a sub 2, multiplied by r to the third power will equal a sub 5. And we can substitute what we know. We know that the second term is 2. That's multiplying by r cubed. We know that the fifth term is 250. So then now, in order to determine that r value, where before I gave you all of the terms, right over here, and you could calculate just by testing every term. Here I'm only giving you 2 of the terms, and you have to determine that r value by looking at how far apart are the terms, and then you solve the equation that's there, that we wrote out. So I'm going to divide 2 out of both sides of this problem. R to the third will equal 125. And then in order to get rid of this cube, I'm going to cube root both sides of the equation. So r equals 5, which reinforces what we already knew. The problem is we know the r value. That's one of the things we need to know for a sequence, but we also have to know the first term. And so then we need to go backwards, back to our list here, instead of multiplying the second term by r, we are going to divide by r to go backwards on our list to find out what the first term is. So we're doing 2a sub 1 is equal to the second term divided by 5. We don't know the first term, but we know that the second term is 2. So 2 divided by 5 tells us that our first term is 0.4. So now we have the two things we need to write our geometric sequence. All right, and that's pretty much what you're working through. If you're testing, what would the graph of this look like? Then you just have to remember that if we're looking at these terms, right, 1, 2, 3, 4, 5, then these terms are going to increase. There's no way that this graph can touch the x-axis. So we're going to have like some value here, and then there's going to be another value maybe here, and then here, and then here, and then here. What I'm showing you is that this curve is going to start out kind of shallow and then get steeper really fast. I missed that point, but that's okay. So in the end, we're looking at an exponential curve. It's either growing very quickly or it's decaying very quickly. So if your R value is greater than 1, then you're looking at exponential growth. And that's what this graph represents. If your R value is between 0 and 1, so like an R value of 1/2, then your curve is going to be moving the other way. It's going to start high and drop low, and then it's going to kind of flatten out. And technically in a sequence, it's only the points, right? It's only the points. We wouldn't connect them because in a sequence, we only have specific values. It's a discrete situation. So anyway, all right, that's what you're looking at. This is exponential decay. All right, the values are getting smaller, approaching a number, typically 0. All right, so hopefully that makes sense. You can look through this document that I'll share, ask questions, and let me know, if there's anything else that doesn't make sense or any problems you want to talk through specifically, and then I will reset that quiz if you want me to reset that, and you can work through that. Okay, let me know how it goes.